Okay, now I went ahead and built up this crazy mess. Um, Focus. So, it's basically an amplifier like this. So, we're using, I didn't use 1 mega ohm, I used 100K, that's good enough. But you got a source resistor here, and this is what sets, so I don't have to use a negative voltage supply. This is a single supply. Um, you can see, it's drawing 3 milliamps at 12 volts because I wanted to make a 12 volt amplifier so I can get more performance out of it for testing. Um, you know, this is an output capacitor here, 1,000 microfarad, and got 1,000 microfarad input capacitor so that this stuff all, the inputs and outputs will float, so I don't have to worry about crazy offsets and overloading function generators and shit like that, or taking that risk of blowing out my function generator from overdriving it or some crap, who knows. Um, and I use these resistors, and it's kind of hard to see what I'm doing here, but the point is basically this circuit. So, now what I did is I didn't even read the book to do this, but I said, okay, I want to try to make an amplifier like that because I know that's a common technique, you know, because what happens is that this gate, okay, in a quiescent state is essentially at ground level, right? However, we know from our little our little transconductance curve here that like I said, a good bias point is right about if you want a 1 volt input, okay, which I was thinking a 1 volt signal would be the max I'd want to generate, even though you really should keep it less with most of these kinds of amplifiers because they don't have a lot of voltage gain. But your input signal range could vary over a maximum like this range before it started doing weird things distortion wise. But that would give us a 3 milliamp you know current, like we were talking about before. So I just kind of figured, all right, I know, with this resistor here, it's got to basically drop that negative zero point 0.5 volts across it. So it's a single supply, but what we need to do is make the voltage plus 0.75 volts across this resistor. So the gate being tied across ground means the source to gate voltage is actually negative zero point 0.5 volts relative to our source terminal, which is what's important. All right, um, so basically we know we want 3 milliamps going through this, and for it to be minus zero point 0.5 volts at 3 milliamps, right? Um, so getting out my calculator here, it's zero point 0.5 minus 0.003 amps. So, that gives us, 166 ohms for that RS resistor, right? Okay, and since it's at 3 milliamps bias point, a good point, is try to get approximately 6 volts right out of the drain terminal, because that's going to be our output, and that's going to be our Q point, is about halfway, between power rails. So I'm using 12 volts, so 6 volts would be dropped across this drain resistor. All right, so 6 volts divided by 3 milliamps, will give us about 2K. Okay, um, so that would set our Q point, and also a 2K resistor, because remember we calculated that was like a roughly a 3 millisiemen, um, 3 millisiemen transconductance, so that would give us a 3 milliamp range. So, so therefore we should have a roughly 6 volt output swing, across a, 2K resistor. All right, so that should be our compliance range. So in other words, it could be, 4.5 milliamps down to 1.5 milliamps. That's our range, across a resistor. And the device itself, will have a 6 volt drop across it, and that, you know, source resistor. So basically, again, I would expect for a 1 volt input signal, 1 volt per, remember, millisiemen, 3 millisiemens would be 3 milliamps per volt. So if I had a 1 volt input signal, we'd see a 3 milliamp swing on the output. So coincidentally, 3 milliamps is also our bias point. So, but that's a coincidence. So they're not connected. It just happens to work out that way based on what I'm trying to do here. So anyway, this resistor here, this 2K resistor could have, you know, um, like I said, 4.5 milliamps across it times, um, 2,000 ohms, which is 9 volts. Okay, that's its maximum voltage across that resistor, and it could be as little as, 2K times, 1.5 milliamps. So it could be as low as 3 volts. So, that basically is what kind of a swing that resistor, the voltage would have across it, and the device itself, the JFET will make up the difference, in those um, circumstances. Now, of course, in reality, I didn't have any 166 ohm resistors in them, so I used 180 ohm. And um, I put 100K, on across the gate instead of the 1 mega ohm they used. Um, but again, for the source resistor, I used 180 instead of 166, and 2.2K is the resistor I had for the drain. So again, close. There's going to be some variation, and the thing is, about that is that, there's an equation, and if you look at this, okay, that's the actual equation of the drain source. So that's the actual voltage. That would be the our point 0.5 volt, negative point 0.5 volts, and VGS off, is that pinch off voltage, which is, just under 2 volts. So, um, and then our IDSS was that, maximum 5 milliamp current. So, you plug all that in, that gives you an approximate deal, and I actually did that out of curiosity on a spreadsheet. I don't know if you can see it, but, this is right here is the result of that equation. So it predicts 2.6 milliamps based on that formula. So, which is, close to what we're looking at. But again, this is just a formula. This is the real thing. So, at the end of the day, these are the values it suggested that I use. 191 ohms for that one resistor, and for the drain, 2.3K. But in any event, there is no way, if you use a different resistor, even using a formula like that, there is no real good way of going and, okay, since I had a 180 ohm resistor on hand, there's no formula I can actually plug that into, at least not that I'm aware of, and you can get, what your new bias points are going to be, because this is a variable and that's a variable. Well, that's not a variable, that's a constant. And that's a constant, but this is a variable and that's a variable. And there's no place for a resistor in here, even though one could be a function of the other. It's just, you just have no way of predicting what kind of voltage is going to form across that 180 ohm resistor. But you can, what you got to do is do it iteratively. So you got to, like go down to, this point here instead of our minus 1.5 volts. You do this and see what kind of resistor value, and it turns out the resistor values get larger as you go this way. So I know it's going to be somewhere, and actually they get way larger really quick. but it's going to be somewhere around here, so I knew it'd be kind of close enough. So, at any rate, so with all things considered, though, I figured, with a 1 volt input, you get a 6 volt output. That's a gain of 6. So that's what I figured. Now let's see what the results were. And again, so I have my little gain formula, and guess what? Gain of 6. You can see, even though I'm not applying the same voltage, I've got, 5 volts out, and, I'm applying, about 8.6 volts peak to peak input. So that's what we see here. You can see that. So, um, versus 5.3 volts out, but I'm not quite to the 1 volts I was going to apply. I figured I'd start small. And this happened to be good enough, but that's what my little gain equation is predicting, and it looks about right. I actually had to change the scale of this because they're all both at the same scale. This thing was giving me warnings and shit about being over voltage, so that's what it looks like with both of them side by side. So, but switching back to 1 volt, um, that's what we got. So, try to change the focus on this. Feel which direction to turn this. But yeah, so, anyway, yeah, it works out pretty good. Now, what I thought I would do, I haven't done this yet because, I'm testing at a 1 kilohertz base frequency. And the capacitors I chose, they have little formulas here in this book, which tells you for design, what to kind of do, although they're not dealing with gain or anything yet at this point. An analysis, but there's a little capacitor formula here. This capacitor, and depends on what frequency you want to put into it. Now I used 100 microfarads, so there's going to be a gain penalty for that. Again, I used 1,000 microfarads for the input and output, which aren't shown here, but so at least that won't be a factor, But at any rate, I thought I would try because I haven't done this yet. I need to get some kind of tripod for this thing. But I thought I would try doing a. By the way, this is yet another scope and waveform generator. So, but I just needed one channel because I just need one channel for the signal input for this, and my 2 scope probes. So you can see which one's input and output. Anyway, I thought I'd go try something that was really fun that I wish I would have made videos about, but didn't. And that's their network analyzer. Because this is actually a great little thing to use for amplifiers. So I got to remember how to set it back up. Let's see, source. One kilohertz here. We can start at that, and let's do it to 1 megahertz, I guess. Let's see. But let me go ahead and get this set up to refresh my memory on it. Because I'm not really sure I've got the scope probe set up in the right order. Let me just run a single and see what it does. Out of range. So, let's see. Okay. Alright, yeah, let me hit pause for a second. Okay, yeah, I forgot. It's been a week since I used this thing, and that was the first time. But yeah, you got to make sure you set your amplitude right. I had it set to 2 volts by default, so that was overpowering the amplifier and giving really low gains. But you can see right here, from 1 kilohertz, certainly, you know, you can see it says, C1 gain 5.9. So again, it's about a gain of 10, and right around, 200 kilohertz or so, it starts to fall off. So it's probably down by, 3 decibels about here or so, about 500 kilohertz, like it says on that marker right there. So anyway, that's one of the cool things you can do. But like I said, the amplifiers like this aren't very high gain. Usually you only use a JFET, if you're wanting to, um, you know, for high input impedance, really. And well, still got good frequency response even at 100 hertz. That's good. But usually that's why you want to use it, and then you usually take that and put it through some other amplifier. So, but there are tricks you can do. Look at Elliott Sound Products on their JFET stuff, and you can use constant current sources and some things like that to to get you know increased performance. But if you need it, there are just a lot of tricks you can play, including code and everything. Um, but overall, this is still the basics of it. So it's a good way to get understanding. So, huh, stupid out of range message popped up again. What the hell gets what kind of bug gets in this thing's ass every now and then, and why? But anyway, so it's actually got performance down to 10 hertz. It's still got a gain of 5. So even with that wrong value capacitor, so it's calculating 8 millifarad for geez, I guess a 40 hertz signal or 10 hertz signal, I guess it was. So yeah, but I guess 100 microfarad worked okay-ish. Better than I would have expected. But anyway, so yeah, you can actually test this thing up to amplifiers with this thing. Start at 1 kilohertz, so it's faster. But up to like, let's see what it looks like at 10 megahertz. Oh, smash! So yeah, that got pretty freaky right there. Um, it's very interesting, in fact. The input signal would do that. Probably has something to do with that capacitor or something. Yeah, the gain on this started really going through the roof. Huh, interesting. Anyway, but yeah, so there's that.